Hey everybody, and welcome to this short walkthrough of rdom. I'm going to be showing you all the code today, and we're going to go through each of these modules one by one. So let's look at the dependencies, I guess, actually first. So, okay, we've got downcast rs, and that is used for kind of like the casting between different types of nodes. And we've got node and element, and then there will be more in the future, but we will want to dynamically cast between those. Lazy static, I actually don't know if we're still using that. Okay, yeah, we're not. And then paste, that's used for some macro syntax combination. And then this error is used for an error. And yeah, actually this is a good place to start. So these are the various different types of errors that can occur. Actually, some of these don't necessarily occur. Yeah, out of memory, it does not seem to be used right now. I think that was going to be, yeah, this one's actually deprecated. This one is what happens when a sandbox is dropped. So in rdom, because we have this giant doubly linked list and tree structure, which is the DOM, the child elements, parent elements, we want to avoid memory leaks, which are fairly easy to have when you have these like cyclical references like we do. And so, yeah, maybe actually we should come back to that because we haven't gotten into how the nodes are cyclical yet. Maybe let's start in the window module. So this is just what you get when you create a sandbox. And actually, let's look at the tests where this is done. So inside the sandbox, we clone it, and then we get a window, and that window function is what returns this window structure right here. And so when it's created, we use this new cyclic feature, which is Rust's way of supporting cyclical tree structures without using unsafe code. So we can create a cyclical structure here, and we do that. So the way that this works is that you get, how does this work? So, oh yeah, so this function will return a value that gets wrapped in an arc, and then this value that we're given, this is what will be the weak pointer to that arc. So we are allowed to use this weak pointer basically before the arc is created. And don't ask me how that works because it seems like magic, but luckily we are allowed to do it. And so we create the document, and the document has a document storage structure inside of it that we create, and we pass that weak pointer into it. And that is what allows the pointer to kind of point up. So the way that this structure works is that we have like a parent node, and that has a strong arc. This is a pointer. There's a strong pointer to some child node, and the child node has a weak arc pointing up to it. So this is the cycle that we're talking about. So we've got this parent node, strong going down, and then weak going up. And the reason for that is that if the parent gets dropped, we don't want the child to have a strong reference to the parent, keeping it alive after the parent's been dropped. So once the parent's dropped, like all of this should go away, really. But definitely the parent should go away. So that is what stops this from being a just cycle of memory leaks. Okay, and then there's the document attribute that just gets the field out of the struct. Pretty much all structs have this context field just because it's probably easier to have it on everything and not need it, as opposed to not having it and then having to go plumb it in later on when we realize we need it. So, and I think we might need it for pretty much everything anyways. So this is something that there is an issue out for putting it into a trait so that it's kind of guaranteed to be on everything. But right now it's just in the struct definition for everything. And then, yeah, we got this document, which is, again, a strong pointer down to the document. All the pointers going down the tree are strong pointers, and all the pointers going up or to the side or our weak pointers. Okay, and so now if we go back to our test, we got a sandbox. So let's see, where do we create a sandbox? This is a sandbox, and it's got that same cyclic thing going on. And we just create the window with this weak pointer to the sandbox, and then we return the sandbox struct, and it works basically the same way as window. Now, let's see, where else can we go? Let's maybe look at a node. And maybe, so let's see, where do we create a node here? So the window has a document, and the document is a node. So let's see how that's created. So we do a document : new, and that has a storage. So what is a storage thing? Let's just go look at where that's defined. So here, and this is node/mod.rs, and we got a document. This is where we define each node. It's kind of like each of these little parenthesized sections are a single node definition, type of node rather. And this is all about to be replaced with some slightly more sophisticated or less sophisticated, depending on how you look at it, macro logic that will hopefully be more flexible at least. But yeah, so here's where we define the attribute nodes, text nodes. This is like just raw text in the document, and then document itself, which is the root document node. And these are for like documentation link into like MDN documentation, and then this is a blurb that just goes in the RDoc documentation, or rdom documentation rather. And storage is whatever we want it to be, really. It's like custom for each type of node. And so like up here in Adder, it doesn't have an actual storage yet. It will eventually, but it doesn't right now. And all these other ones are used here. Okay, so document storage is just a weak pointer back up to the window because not everything has a pointer up. Well, we decide that we want a pointer in the document back to the window, which it's not guaranteed that there will be. Actually, I guess there is. Every node has a parent pointer, or should eventually, but right now it's defined here. It's dubious whether this actually needs to be here. Maybe this could be a method instead, or a method in the impl. But instead it's a field. And for text node storage, this is a string just for the text that needs to be stored in that particular node. And up here, so these are our storage implementations, storage definitions rather. And up here is where the actual like meat of each definition for a node happens. So before I go here, because it's pretty complicated, I just want to go up and look at these traits as well. So we've got input event. That's not used anywhere, I don't think, no. But someday it will, because I think it's like a superclass, just like node and element. Any node is a trait. It's called any node because we have another node, or another struct that's called node, and that just represents like an abstract node as opposed to the trait. So it's a node is a struct, and then any node is a trait. And this just covers what all the functionality that is common to all nodes is. So we've got like get context, and context is the same thing as a sandbox. It's probably should land on one of those names to use instead of having two. Cloning the node, this just takes our node and gives us a new node that is identical for some definition of identical. It's not really the same node because it creates a new node, but the DOM spec has some behavior for what clone means. So that's why we have our own clone method as well, because it's not the same as like Rust's default. It's not the same as this clone behavior necessarily. Maybe it's functionally identical, but we can't guarantee that for every type of element. So first child, kind of self-explanatory, gives you a reference to the first child. Last child, same. Append child will add a child to the node. and child nodes gives you a reference to a node list, which we haven't gone over yet, and that is one of the rare structures that are not nodes in rdom. Right now, most of the structures I would say are nodes, and probably in the future most of them will be nodes and elements. But NodeList is one of the few that's not an actual node. And then impl downcast. So what this does is okay, I can't tell you exactly what it does, but it sets up downcast RS for this trait. And as you can see, we have to inherit from downcast sync for that. So these two go together, downcast sync in this. And the reason that we have downcast on this is because we want to be able to downcast from a node to an element. Anytime you have a reference to an element, you can cast it to a node, just in most DOM implementations. And so we want to be able to do the same, just like you can do with WebSys. You can cast an element to a node, and then if you have a node, if it's an element as well, then you can cast to an element. But that downcast could fail if it's a node that's not an element. For instance, if it's an attribute node, you would not be able to cast it successfully to an element because it's not an element. And okay, so now we've got our macro rules for this impl nodes macro. And I am kind of hesitant to even go over this because it's going to change soon, but we should do it anyways. So really what this says is that each of these blocks matches what we define down here. So we see a type and then the word storage and then some other type, and that corresponds to here. So we've got type, which is a type, storage, and then we name it storage. This is the word storage, and this is the actual type. And then this is the type of the type, which is type. It's a little meta. And then blurb, this is going to be like in the documentation. So here we concatenate it with this string to build the documentation string. And then link goes inside this link to MDN. Postlude is like, for some things, we want to have like a little explanatory text, but we don't do it anywhere here. We do it in elements later on. And here's the actual definition. As you can see, we used paste and that's necessary to do this kind of concatenation. Paste also lets you combine types with others, kind of like fragments of identifiers. So it's handy for that. We don't really need these to be separate paste blocks, but I figured it'd be nice to keep them self-contained, as small as possible. And then, so yeah, this is the definition of the actual type. So for each node, we're going to define a struct called that node so text node would be pub struct text node. And then that will contain context, which is a weak pointer back up to the sandbox. Node behavior, which is kind of like a encapsulation of some fields and traits that each node implements. And then storage, which is whatever storage type we specified. For very simple types, this will just be empty tuple. And so for the actual implementation of this struct, it's just impl of that type, there's going to be a new function, and this will return a strong pointer to the type, or rather to the struct that we just defined. So it'll always return an arc to that pointer, so a strong pointer. And yeah, always takes a context, always takes a storage, even if it's just like default. We could, if we don't have a storage to specify, we can just say default : default, and it will, like, for empty tuple, it will turn into like empty tuple, which is just empties, no data. So, and then we do another cyclic construction. Rest here is for any extra things that we want to add to the impl block. And you can see up here, it is defined inside of the impl block that's inside of our definitions. So anything that goes inside this impl block, that is considered rest, and then rest gets spread here. Down in any node, so because this is definitely a node that we're defining, we want to implement any node for it. And it just, most of these are like proxies to the node behavior because that's common to all the nodes. But, and it's, I think this one can't be done because of the usage of type right there. And node behavior is not generic, so it doesn't have the type. But clone, so really what it's just doing is taking the type and then it's calling new on that type. And as you can see, it just uses the default storage for now. Whether we'll always be able to get away with this is up for debate. It's unclear at the moment. So, but yeah, all this should be storage. Yeah, we're just cloning the storage there. And then private any node. This is for, so private any node is a special trait that's just like any node, except that it contains the function calls that we don't need to expose to the outside world for people who are consuming rdom. In fact, like if they were able to get access to it, then it would be probably not in their best interest because, yeah, it's just functionality that's private to this package. And like the usage of it is not supposed to be understandable or, yeah, not the concern of the user. So we hide it in this special trait that's not public. And again, it just proxies to node behavior in this case. There will probably be more things that go in here. Anytime we add a new behavior, probably, although, yeah, I don't know whether we would actually add one to private any node. It's debatable. We'll probably have a private any element for when we have get element behavior. Although, again, all this is possibly going to change soon, so we might not have these proxies at all. In fact, that would be ideal if we could avoid that. Okay. So we just looked at mod, and here's the private. It's nothing really interesting there. Element, this is just like the node file, except that it is about elements instead. We still have all the node behavior stuff because all elements are nodes. But we also have this import any element, which right now doesn't have any functionality associated with it. Soon, or someday, it will have the things that you would need to do for an element, like query selector probably, and query selector all, create element perhaps. Yeah, I'm not sure what things are specific to element, but yeah, you would find them by going to MDN and searching for like element. There's all kinds of specs around that. But other than that, yeah, it looks basically the exact same. And hopefully we can eliminate some of this boilerplate in the future. But yeah, so here's where we define some elements. So this is the HTML element, the root HTML element that goes in the top of the document. Body element, kind of self-explanatory. And then just for funsies, button element to see if we can create a button. And none of these elements do anything yet, so it's all work in progress. And yeah, everything we've looked at so far is considered a core representation. So we've got core nodes and core elements, but in contrast to core, there's also the nice elements and nice nodes. And there's this description here of why that is. The nice interface is just considered, it's supposed to be something that the outside world can consume that is a little bit more similar to interacting with WebSys. And the way that it's more similar is that we are wrapping the arc so that they don't have to deal with the arc by themselves. It's just automatically consumed. How useful this is debatable. And we might decide that it's not that big of a deal to deal with the arcs and just delete all of this in the future. But I feel somewhat strongly that it will be wanted, especially just like, yeah, you don't want to be unwrapping all the time or cloning and then calling things on it. So I don't know. Maybe it won't be that bad, but it would be nice to emulate WebSys if we can. But yeah, this also might get unwieldy just because there's a lot of stuff that we would have to copy and proxy to. So might be best to auto-generate this if possible. Yeah, these are pretty similar to the other nodes and elements and stuff, but there's a lot less functionality here because it just proxies to the other things. One thing that we do here is casting. I don't know if we had this in the raw nodes, but so this would like cast from an element to this is casting from an element to a specific implementation of element. So casts from the this is like the abstract element. So up here we have an abstract element which just contains a dyne reference to any element. Something that implements this any element trait. And so this could be like HTML element, body element, any of those things. But this reference, if you have a reference to this, that just means that you don't know what type it is. It could be any of those things. And so that's why we would have this from and try from, so we can go from this type to element, no problem. There's this, that can never fail because all button elements, for example, are elements. But if we try to go from element to button element, what if that element is not a button element? Then that will fail. So that's why this returns results. So we try to do a downcast to the type that we're casting to, but and then we try to create a new, I guess. Okay, so let's actually look at what this does. So this is a little bit complicated. So up here we got an element, and then we look at the 0, which is like the thing wrapped inside of the element. So this is the arc right here. So this is element.0 is the arc. And then we're casting to core type. Okay, so we've got the wrapped type and we're casting the arc inside of the wrapped type. Wrapped, when I say wrapped, I mean nice. We have the nice type, the arc inside of the nice type, and we are casting that to the non-nice type, so the core type corresponding to. So if we had a nice HTML button element, we're casting to a core HTML button element. And if that works, we're going to map the results of that, map the value that was returned by that into the type defined here, which is what we're trying to cast it into, right? So from element to button element. So we're taking that downcasted arc and we are creating a struct from that. And then if it fails, we're going to just return the original element. So we're going to construct an element instead of that new type. So basically, if it fails, we're just going to return the original element. And yeah, that's how that works. Anything interesting here? Pretty much the same thing as element, nice element. These are just nice nodes. A little bit duplicative. The fact that all this is unused is just a function of the fact that we don't have any tests using it. Yeah, we should really do that, I guess. But query selector, this is kind of where I started to implement some query selector stuff, but really doesn't do anything yet, just returns error all the time. So it doesn't actually do anything. Here's something somewhat interesting. In a few cases where we need to access the context, the sandbox that is, or just as a guard before we do something that might involve other elements in the tree, we do a check real quick to see if the tree is like still around. Because if the tree was dropped and we're trying to do something on the tree, that's obviously going to fail. So it would be nice to return a nicer error message. So that's why we return this sandbox dropped. Okay, behavior. So I tried to create a struct for each superclass, and that's defined in the DOM spec. So ParentNode, that's one of them, but it doesn't have any functionality associated with it yet. And yeah, nothing uses this yet, but theoretically something will need stuff that ParentNode does. So, but element is it's one of those things. So we've got element behavior defined here. Again, nothing uses this yet because we don't have any special element specific functionality, but we do have node behavior. And so yeah, here's just a bunch of implements of a bunch of node functionalities, common to all nodes. Because we need a certain number of pointers, this is a storage that, or it's not called a storage, but it's stored inside of the node behavior. So, so this is where we have our data that's associated with these traits. And the reason that these behaviors are separated like this is because, and they're not traits, is because traits cannot specify these fields. Yeah, I know there's an issue out for kind of changing the way this works, and it will depend on what the experiment looks like with the macro rewrite that I'm working on, how we end up dealing with this eventually. Hopefully it'll be nice, whatever happens. Okay, so node, that is just so like if you think of the DOM as being kind of like a parent node, which is like document, and then you have maybe a body, and then you have like a button, 2 buttons maybe. Each of these buttons has a node behavior. And these aren't actually part of the DOM. This is just, they're only children in the sense that our DOM knows that they're children, considers them children. So if we have code that's in this node behavior and we need to access something about the button, that's why we need this pointer back up to the node. So yeah, reference back up to the core node, although it is a weak pointer because, again, anything that's not pointed down is supposed to be a weak pointer to avoid those memory leaks. Parent node, this is a pointer to the node that's above this node. Pointer to the node that is to the left of this node, to the left of this node rather, to the right of this node, right sibling. And then child nodes is a list of all nodes that are children of this node. Again, even though this is a child in RDOM's world of the node, it is not, node behavior is not a node. So it is not considered to be part of the child nodes. Okay, so this is just a constructor. Should be pretty straightforward. It's just all empty values. First child. So the reason that this is in a read-write lock is just because of threading. And I forget exactly what the error was that was popping up with this, but yeah, it was necessary. So if you want to see what happens when it's not there, feel free to delete it and just like see what happens when it compiles. It was required because like I think it's because like when you're running code that accesses this, there's no guarantee that you have exclusive access to these child nodes. So you don't own the child nodes, so you have to like make sure that you can get an exclusive lock on it first before changing it. And we do change it in append child. So it's probably that you can't get an exclusive mutable reference to that vector without the read-write lock. So yeah, so that's what we do here. We call write, and that is what gives us the mutable lock results. I guess that's what they call it. But yeah, it's what lets us write to this list of child nodes. Everywhere else we use read. And interestingly, like the reference to the node behavior actually doesn't have to be mutable. So we can get a mutable reference to this child node's structure, even though self is not mutable, which I find is pretty interesting. So you don't have to have if you create a node and you don't use the mute keyword, you can still add children to that node. Static child nodes, this is kind of it gives you a direct list of the child nodes, but because that is not something that we should be exposing, we have a side, kind of like a sister method that does a similar thing, but it returns the appropriate consumable, like public safe structure instead. So this is purely for internal use, and this is actually public. And you can see in the node, if we go back to node, so over here, we have a function for child nodes, and that just calls the node behavior child nodes, but we don't have one for static child nodes. So that's the deal with it. Even though these are both have the same visibility, this one is proxied, but the other one is not. So this one is purely internal. There should probably be a comment up here actually about that actually, but okay. Oh, I think it's probably in the, never mind. I was gonna say it's in this trait, but there is no trait for this. Okay, child nodes. So when you call child nodes in the DOM, you receive a node list. And there's two different kinds of node lists, even though they're both under the same name. There's live node lists and static node lists. And yeah, here's the documentation. So a live node list is dynamically defined. So it will change based on the state of the DOM, the latest state of the DOM. If you get a node list from a function and then something about the DOM changes, that value will change that you got. If you have a static node list, however, it will, after you gotten it, it will stay the same, basically, or at least at one level. There's no guarantees that the elements inside of the node lists won't have their contents changed, but the actual list of nodes themselves is constant. And actually thinking about that right now, I'm not 100% sure that a static node list won't be completely static. So that's something maybe interesting to look into, like at all levels. So there's like the one level of mutability, and then there's like infinite levels of mutability. And in Rust, like you can maybe guarantee that your particular top level is immutable, but that doesn't say anything about interior mutability. So, so that's kind of the same thing with node list, static node list, is that if it's static, that all that means is that the items directly inside the node list won't change, but the items below that might change, for instance. But anyways, here we're creating a live node list, and the way that we do that is we kind of specify a query. This is almost like defining a SQL query. So we say what kind of live node list we're defining, and the answer is that we're defining a child nodes node list. And we go in here, you can see these are the different types of node list storage node list storages, and there's static, which is again just a list of nodes. And then there's live, which could be any one of these things. Right now, there's just one type of live node list, but there could be more in the future. So child nodes is not the only type. And what child nodes consists of is just a list of, or is a reference to the thing that these child nodes are of. So this doesn't actually contain any information really. As to the results of this. It's kind of like a layer of indirection. So all it says is what we want the result to be, how to look up the result, basically. So it's like a declarative, how do we figure out what the result of this node list is, what the values of this node list are. And up here is where the actual resolution of that query happens. So whenever you do anything to a node list, like get its length, or let's just consider getting a length. It has to check to see if it's a static node list or if it's a live node list. If it's a static node list, then it's pretty simple. You just look at the list and then it's the length, because all static node lists have a vector inside of them, and that's what the static node list is. But with a live node list, it's more complicated because the query represents just a declaration of what you want. It doesn't actually contain the information. So we have to see what kind of query it is, and in this case, the child nodes, because that's the only one there is right now. But in the future, this might have more arms. And if it's a child nodes, we look at this, what we want it to be, what we want to look up the children of, and we just kind of access the this other this is the private method we were talking about, the StaticChildNodes function. And so we're dynamically here. When you get the length, we go in and look at the node, get its child nodes, count the child nodes right then and there. So even though it looks like you got a node list and that was when the work was done, really the work is done when you call length. And that's what makes it a live node list. So it's lazy evaluation. Same with item. If you get an item, this is just like with an index. I think item and get are the same thing. As far as I can tell, that's what the DOM spec says, but yeah, still to be determined, I suppose. But yeah, if it's static, NodeList, simple, just like before. We just get an index, but if it's live, then there's more work to be done. Okay, named NodeMap. So this is another structure, just like the NodeList, that is not actually a node. So named NodeMap is not a node, it's a NodeMap. And all that means is that although it belongs to a node, like an element in this case, it really does not take up space in the strict DOM hierarchy. I'm not sure about the terminology there, but yeah, it's not a node, so it's not considered like a child node. It's just an annotation basically on a node. And actually, I think it belongs only to elements. So I don't think you can have a named node map on just any node. It has to be an element. And it has a context reference just like everything else. And attribute list. What this is all defined in the DOM spec up here. But basically, the way attributes are stored in the DOM is that you have a giant linear list of the attributes and their values. So anytime you get an attribute, it's actually doing a linear search through the DOM to see what the first matching attribute node is. And so the attribute list is a list of attrinodes, arcs of attrinodes rather. And so to write all this code, it's going to have to access things that are stored in attrinode, which are not defined right now, but in the future they will be. Internal prelude, these are just some common imports that we do all over the place, and we'll probably be adding weak and arc to this soon, since we use them in pretty much every file. This is just some configuration that you can specify for when you're creating a sandbox. So like in the future, we're going to have some functions that you can call on like window to get like the inner width and inner height, and probably a few other things. But in order to specify how you want those to behave, we create this screen metric. We have this screen metrics struct. I would like to actually look up what these are called in Gecko and things like that so that we can name them something more standard. I just kind of made this up. And let's see, is there anything else? I think that might be everything. Cool. Well, thanks for looking through this with me. I guess the only thing left is this new CI pipeline, which we have. Yeah, thank you all for your contributions. This project is growing pretty quickly, and I'm excited for the future.